We are going to review acids, bases, and pH. I've shown here some common household acids such as lemon, orange, vinegar, and cleaning solution such as HCl. What all acids have in common is that they are proton donors. A proton is a hydrogen atom that has lost or donated its one electron. Recall, a hydrogen atom consists of one electron and one proton. So if you remove the electron, then you are left with the one proton. Hence, it is a proton donor. For example, take hydrochloric acid, or HCl. When it dissolves in water, it will separate or dissociate into a proton, which is the H with the positive, and a chlorine atom, which is Cl with the negative. Since all acids are proton donors, they will increase the amount of protons in a solution, or in other words, it will increase the acidity of the solution. And we will relate that to the pH scale later. Next, let's talk about bases. I've shown here some common household bases such as bleach, sodium hydroxide or lye, which is found in bar soaps, and ammonia. All bases are proton acceptors. Take, for example, sodium hydroxide or NaOH. When NaOH dissolves in water, it dissociates into a sodium cation, which is a positive charge, and an OH anion, which is a negative charge. Now take that anion with a negative charge and combine it with the proton, and hopefully you'll see that it forms H2O, or water. So the negative anion finds or accepts the positive proton, because as you recall, opposites attract. Ultimately, bases will decrease the amount of protons in a solution because they bind or accept to those protons. And we will also relate that to the pH scale. Now, let's look at the pH scale. pH can stand for power of hydrogen. So it measures the amount of hydrogen ions or protons in a solution. The scale runs from 0 to 14, and you might recall from chemistry, it's a logarithmic scale, meaning it moves in powers of 10. 0 is the most acidic, 7 is neutral, such as pure water, and 14 is the most basic. So if you look at our scale, it runs from 0 to 14, and you start at 7, which is neutral pure water, and you move more basic, you'll see you reach things like egg white at 8, toothpaste at 10, ammonia at 11, bleach at 12 to 13. So as you move closer to 14, you get more basic. In the opposite direction, as you move from 7 to 0, you get more acidic. So for example, we get down to urine and tea and coffee at around 5, orange juice at around 3, gastric fluid, which is in your stomach, at around 1, down to battery acid. So the closer you get to 0, the more acidic you are. Now, importantly, let's talk about buffers. They are chemicals that resist pH change by making a solution more basic or acidic as needed. And they're extremely important because they help your body maintain homeostasis, or a properly balanced pH. Take blood, for example. Your blood should be at a pH of 7.4, which is slightly basic. Remember, anything above 7.0 is basic. And your blood pH has to be very specific. It can only be 0.05 off from 7.4. In other words, in the narrow window of 7.35 to 7.45. So it's very critical to keep your blood pH in homeostasis. The bicarbonate buffer system helps you do that. It consists of carbonic acid, which is H2CO3, and If, for example, your blood is too basic, in other words, above 7.45, carbonic acid can dissociate and give off a hydrogen ion. So you'll see that right here. And that will increase the acidity of your blood, or in other words, bring back down the pH. In the opposite direction, if your blood pH becomes too acidic, so if it drops below 7.35, your bicarbonate buffer system can then make more carbonic acid and therefore eliminate more hydrogen ions, making your blood less acidic and bringing it back into the homeostasis range. So that's the hallmark of a good buffer. Again, it can make the solution, such as blood, more basic or acidic as needed, keeping your body in homeostasis in terms of pH.